Hi children, how are you? I hope you are doing well. Today here we with another topic, Lorentz Force, which is an important part of moving charges and magnetism. So let us start about what is this Lorentz Force. This is Sudhir Kumar from physics classes. Sudhir physics classes. Now before going to this Lorentz Force, let us say few points which you know already because we require here. Suppose if you have electric field here like this is an electric field. Suppose you are having a charge Q inside the electric field of strength E. Then this positive charge experiences the force EQ in the direction of field. And if we keep a negative charge, it will experience the force EQ opposite to the field. Let us not go much detail into this because we require this. But anyhow, if you go into this consideration, suppose if this is a positive plate, very long plate let us say, and this is a negative plate, a long plate, then there will be an electric field between positive plate to negative plate. A uniform electric field will exist. Naturally, a positive charge will be attracted towards negative plate and negative charge will be attracted towards a positive plate. So therefore, they move opposite direction. Positive charge in the direction of field, negative charge opposite to the field. And this force acting on a particle causes an acceleration. That is why we can equate this force equal to ma. So what is the acceleration of the particle now? This is eq by m. Therefore, these two particles are moving with this acceleration in opposite direction. Remember, positive charge in the direction of field, force is experiencing. Negative charge opposite to the field, the force is existing. And the force is equal to how much only? The force is equal to EQ. Of course, that is in turn equal to ma. This is one information you are supposed to know before you go to Lorentz force. Next, you have a magnetic field now. Let us say I will take a magnetic field like this. In the same manner I will take, no problem. This is a magnetic field existing in this region. You can imagine a north pole here and a south pole here of a magnet. Okay, then you will be getting a magnetic field between the poles. Now, a charged particle of charge Q and mass m is entering the field with a velocity v. So v bar makes an angle theta with the b bar. Then the force acting F bar is equal to Q into v bar cross b bar, or F is equal to BQV sin theta is the force acting on the particle. Of course, the force will be in a direction of v bar cross b bar. Or there is one more case I'll take. Suppose if the magnetic field is into the board. The magnetic field is into the board, b bar. Now a particle enters the magnetic field now. Definitely it is entering at an angle 90 degrees. Why? Because the magnetic field is inward, like this, and velocity is upward, like this. Therefore, they are perpendicular to each other. So therefore, the force acting on the particle will be BQV sin 90. And this direction of force is given by Fleming's left-hand rule. Magnetic field, velocity of the positive charge, and force acting on the positive charge. So magnetic field is inward, velocity of the charge is upward, so it bends towards left. Therefore, this particle has to move in a circular motion like this. This is already discussed in the previous lectures. So when a particle enters perpendicular to the magnetic field, it moves in a circular path. How does it move here? It moves in a helical path, isn't it? Because theta is not 90 degrees here. So all this information you are supposed to know. Then we come to the Lorentz force now. So let us see what is this Lorentz force. If electric and magnetic fields are existing simultaneously at the same place, then how does the particle experiences the forces? In which path the particle will be moving? And that is our discussion here. So let us take now, it happens that there is a magnetic field in this region. Let me take like this. This is a magnetic field. B bar. There is electric field in this region. Okay. Let me take. This is electric field in this region. Both fields are there. So in both fields now, let us say a particle is entering. Okay. At an angle some theta. The particle is experiencing both forces now. Magnetic field will do its work. Electric field will do its work. Both of them will exert force on the charged particle. They exert independently. So magnetic field will not leave because electric field is there, or electric field will not leave because magnetic field is there. They do their own work. So the total force on the particle is known as Lorentz force. This is called Lorentz force. That is force due to magnetic field plus force due to electric field. So force due to magnetic field is Q into V bar cross B bar. Force due to electric field is E bar into Q. So if you take that, okay, you take Q common here. This is V bar cross B bar plus E bar. So this total force acting on the particle, so the resultant force which is acting on the particle, okay, is known as Lorentz force. This is the most appropriate equation for you. So force due to magnetic field and force due to electric field. This total force, okay, here bar is there. This total force is known as Lorentz force. So sum of the forces exerted by the magnetic field and as well as the electric field, the vectorial sum is known as Lorentz force. So this is the definition of Lorentz force and this is the formula. But when you go to the competitive exams, there are so many applications. Let us see one by one, we will discuss now few of them. There will be so many cases, but which are appropriate for the exam, only those we will be discussing here. Now let us say there is a magnetic field here. This is B bar. There is electric field also existing in this region. Say this is B bar. Oh, sorry, E bar. Both are there. Now it happens that a particle is entering the magnetic and electric fields which are parallel to each other with some velocity u I'll take, initial velocity, right? When it is entering both fields. So in this case I am taking E bar parallel to B bar. Both fields are there in that region, but both electric and magnetic fields are parallel to each other. See, then there will be so many complications in this discussion also. See, if E bar and B bar are not parallel, if E bar and B bar are at some angle theta, so the discussion will go in different manner. But we will discuss only two cases. If the E bar and B bar are parallel to each other and E bar and B bar are perpendicular to each other, we will discuss. But if you want, you can also discuss that if the fields are in opposite direction, if the fields are at some angle theta and particle is entering at some angle, oh, there is a lot of discussion on this. It's never ending process. Few cases which are important we will do. 9. In this case, what happens? Force due to magnetic field, let me calculate. So, force due to magnetic field is BQV sine 0. Why? The particle is entering, V means here U only, of course velocity with what it is entering. Now we are in U, same here. So it is parallel to B. So the velocity with which is entering parallel to B. So V bar and B bar are parallel. Therefore the angle between V bar and B bar is 0. Therefore sine 0. So force due to magnetic field is 0. So there is no effect of magnetic field if a particle is entering parallel to the fields. Magnetic field is not affecting. So you can leave that part. Then what is the force due to electric field now? I have told you already, remember. The force is equal to EQ. And the particle is now experiencing a force after entering the field. Which field? Electric field. Due to magnetic field, no effect. I have already discussed. So only electric field is affecting. So let us discuss that. And this force causes acceleration in the particle. M into A along x-axis. Acceleration will be along x-axis because the force EQ also acts along x-axis. So this particle will experience a force EQ along x-axis when it is entering with velocity u into the field. Therefore, acceleration is also along x-axis. So I have equated F is equal to ma, where F is equal to EQ. Therefore, the acceleration along x-axis is nothing but EQ by m. Right. Now, it will travel for some time like this. It will acquire a velocity v after traveling some distance for some time t. So, it has traveled a distance, yes, for a time t. Therefore, it has acquired a final velocity v. Its velocity is increased. The magnitude of the velocity is increased. Then I can write v is equal to u plus, u is of course along x-axis only, u plus at. A is this. This will be the velocity after the time t seconds. How much distance it has traveled along x-axis? Of course, this velocity is along x-axis only because everything is acting along x-axis. The distance traveled along x-axis is equal to ut plus half a into t square. That is nothing but acceleration along x-axis. So distance traveled along x-axis, this is half EQ by m into t square. So what is the question they will ask in this exam? If a particle is entering parallel to the electric and magnetic fields, which they are again parallel, then what is the effect of magnetic field? 0. What is the effect of electric field? It causes an acceleration EQ by m along x-axis. Next, and what is the path of the particle? In fact, it is a straight line. The path of the particle is straight line. And what is the final velocity after t seconds? What is the distance traveled after t seconds? So these are the questions they'll ask in this case. One more. Sometimes the particle here velocity, initial velocity is 0. So what? You put u0, you put u0 here. What happens in that case? In that case, if initial velocity is 0, then the velocity is just EQ by m into t. Similarly, the distance traveled is equal to half EQ by m into t square. That's all. But the particle will go in straight line only. But only thing is that it starts from rest. So two questions can be asked. When it is at rest, when it starts from rest, when it does not start from rest. In both cases, it goes in straight line. Right? Now, the next case. If at all, the particle enters perpendicular to the field. Perpendicular to the field. See, perpendicular, both, no doubt, here magnetic field, I will take little bit length here. Magnetic field, right? And electric field Both are parallel, no doubt. E bar parallel to B bar, no doubt. But the particle is entering perpendicular to the fields. That is what happening. Say now the particle is coming like this. It enters perpendicular to the field. Say with velocity v. So I want just a minute, Amma. Say with velocity u I'll take. V or u, anything, velocity, that's all. This is the velocity with which it is entering. Now what happens, you think? Anyhow, electric field will try to pull in towards right only always. You know, whenever, in whichever the direction particle enters, the electric field will exert a force in the direction of field only. If it is a positive charge. If it is a negative charge, the force exerted will be opposite to the field. In whichever direction the particle enters, no matter, electric field will always pull in its direction only. That is one point. Second point, what does a magnetic field will do? Now this particle is entering perpendicular to the magnetic field also. Whenever a particle is entering perpendicular to the magnetic field, you know, magnetic field will make a particle to move in a circular motion. And one more important point is that magnetic field can change only the velocity direction. Magnetic field can change only the direction of the velocity. And magnetic field cannot change the magnitude of the velocity. Magnitude of the velocity. So only what does a magnetic field do here? It tries to, because it is entering perpendicular to the magnetic field, it will try to move in a circular motion. So these two forces, no doubt, after entering, the particle will experience two forces. One force, EQ, will act like this, and another force, BQV. Okay? I will not say BQ will be acting. You have to use a rule, isn't it? You cannot put your direction as you like. I am taking EQ in the direction of field only. That is correct. But in order to decide the direction of magnetic field, I have to use Fleming's left hand rule. So this is a magnetic field. This is a velocity. The force will be inward. Yeah. So the force due to magnetic field will be inward. Force due to the magnetic field is inward. The particle which is entering with velocity u perpendicular to the field. So therefore magnetic field will try to move this particle in a circular motion like this. Inward, no? The force is inward. No? So like this. Suppose I'll tell you, for example, this is a magnetic field. So the particle will now enter like this, right? So it will try to move in a circular motion around this. Try to move in a circular motion around this. So it will try to move in a circular motion around this magnetic field. And electric field try to move in along x-axis. So particle has to do a circular motion and particle has to move along x-axis, because electric field will pull along x-axis and magnetic field will try to move in a circular motion which force is acting into the board. So it will rotate like this. So both simultaneously will be acting. So whenever circular motion is taking place and there is a force acting in forward direction EQ, so it will move in forward direction like this. That is called spiral path. I hope you remember, this is a spiral path. So the particle has to move in a spiral path. So the particle will move like this. Spiral path it is going. But like that. It goes. Let me extend this magnetic field. Let me extend this electric field. So what is happening? Let us see now. So the circular motion whose radius r is equal to mv by bq. The circular motion is caused due to the magnetic field. And the radius of the circular motion is mv by bq, but v means the velocity with which is entering here. Perpendicular velocity. So this radius is constant. So everywhere the radius will be constant. But what happens along horizontal velocity? Along horizontal velocity will be increasing. V is equal to u plus at. Therefore, V is equal to, see, initially particle is entering perpendicular to the field, but there is no horizontal velocity here. That is why you have to take 0 here. Afterwards, slowly horizontal velocity will develop. How it will develop? Because of this force EQ. So now slowly horizontal velocity will develop. Initially horizontal velocity is 0. Therefore, the velocity, okay, along x-axis is increasing with time. Velocity along x-axis is increasing with the time. Who is increasing? Electric field is increasing this velocity. What is magnetic field trying to do? It cannot change the direction, it cannot change the magnitude of velocity. Who? Magnetic field. It can change only direction. So magnetic field ज़्यादा से ज़्यादा क्या करता? वो circular motion में rotate करते ही रहता. बस. Because it cannot increase magnitude. So this will happen and this will also happen. Because horizontal velocity is increasing, the pitch will be increasing. So let us say this pitch is P1, say this is P2, this is P3, then I can say P3 greater than P2 greater than P1. So what are your answers? What are the questions? If electric field and magnetic field are parallel to each other, number 1 condition. Number 2, the particle is entering perpendicular to both the fields, that is second condition. Then this particle makes a circular motion and as well as moves forward, hence the path is helical path. Very, very important. The path is helical path. With a constant radius but with increasing pitch. So it moves in helical path. It moves in helical path. With constant radius. With constant radius. Then increasing pitch. With this is your answer. Okay. Next I will take now, particle is not entering with velocity u, it enters some angle. We'll see what happens now. Fine. So, no doubt again in third case also electric field parallel to magnetic field. Both are parallel. Say this is electric field. Say this is magnetic field. Right. Let us say the particle is entering now not parallel, not perpendicular, but makes some angle theta. With velocity u. Anything you can take u, v, v naught, anything. Velocity, with some velocity it will enter. At an angle theta with both magnetic and electric fields. Because they are parallel now, this theta will be applicable for both. Now, what happens? There is a relation between these two here. I'll tell you. First, resolve this velocity. The velocity along x-axis is u cos theta. The velocity along y-axis is u sin theta. So the perpendicular velocity here was u, but here is u sin theta. When it is entering, the horizontal velocity is 0, but it is u cos theta. That is the only difference. Remaining concept same. So again it moves in helical path because this component which is perpendicular to the magnetic field tries to move in a circular motion like this with constant radius. What will be that radius? Same formula only. R is equal to m into u sin theta divided by bq with constant radius. Why? See, mass is not changing, q is not changing, b is not changing, and magnitude of u sin theta is not changing because magnetic field cannot change the magnitude. It can only change the direction. So therefore the radius will remain constant. Next, in horizontal direction, electric field will pull. What is the force along in horizontal direction? EQ. Therefore it causes an acceleration AX, ma. What is the acceleration with which it moves? EQ by m. Okay. What will be the final velocity along x-axis? V is equal to u plus at. But what is u? U cos theta. At. EQ by m into t. Therefore velocity is again increasing in horizontal direction. So therefore pitch will again increase. So same motion will take place. Okay. So the particle moves like this with increasing pitch. Let us say this magnetic field, electric fields are there. So this will be P1, this will be P2, this will be P3, right? So again P3 will be greater than P2 will be greater than P1. So what is the questions again here? Whether it is enter perpendicular to the fields, whether it enters at an angle theta with the fields, in both cases, they travel with increasing pitch. They travel with constant, they do circular motion with constant radius. And their horizontal velocity will be continuously increasing. So they move in a helical path with increasing pitch. So common answer you have here. Right. Now the last and the most important. These two will be perpendicular now. This is very, very important. In many competitive exams, they were asking on questions when electric and magnetic fields are perpendicular to each other and the particle is also again entering perpendicular to them. Both fields. And the velocity is also perpendicular. Okay. Magnetic fields are also perpendicular. Right? Okay. I will take now magnetic field. The electric field perpendicular to magnetic field. So magnetic field I will take into the board. This is a magnetic field into the board B bar. Electric field I will take vertically downwards. So here E bar is perpendicular to B bar. Why? The electric field is inward. Magnetic field is down. Magnetic field is inward. Electric field is downward. So they are perpendicular. Now particle is entering now. Particle is entering now. Like this. I will take velocity V only here now. Not U. I will take V. I told it is velocity. I can put any name V, U, V naught, anything as I like. So V I am putting now. My wish. Now you see this velocity is perpendicular to the magnetic field, electric field. It is perpendicular to electric field and it is also perpendicular to magnetic field. Magnetic field is inward, so it is coming perpendicular to that. Electric field is downwards, it is coming perpendicular to that. So therefore, here the velocity is perpendicular to electric field, velocity is perpendicular to magnetic field. All these three conditions are satisfied. At this condition, he will ask us the questions. Okay. Let me calculate the forces on this. Lorentz force, both electric and magnetic forces. So electric force will be acting downwards because this is a positive charge only. Generally, if I don't mention, it is positive charge. It will experience a force in the direction of field EQ. So the force EQ will act downwards. Next, force due to magnetic field. Let me calculate the Fleming's left hand rule. Magnetic field, velocity, force. First you take these two. So magnetic field is inward. Velocity is along positive x-axis. There is a force now in upward direction due to magnetic field, and hence it will experience the force in upward direction due to magnetic field, which is BQV sine 90. So first condition, if force due to magnetic field is equal to force due to electric field in case, then what happens? They get cancelled. When both forces are cancelling, see, some particle is going like this, you are applying 10 newtons upwards, 10 newtons downwards, for example I am telling. So both forces cancel, then it won't go in any direction, go straight. So if these two forces are equal, they are equal and opposite, so they get cancelled. So this particle does not experience any force, and then in that case it will go in straight line. So the particle travel in straight line. I'll put the equations. B Q V sine 90 is equal to EQ. Magnitudes of the forces are equal, but they are acting in opposite direction. So Q gets cancelled, and the velocity is the ratio of electric and magnetic fields. This is very, very important. So if electric and magnetic fields are perpendicular to each other, and if the velocity is perpendicular to the electric field and as well as magnetic field, if at all the particle is going in straight line, it means that the forces are getting cancelled and their magnitudes will be equal. Then the velocity with which it travels with a constant, the velocity will be equal to the ratio of the electric and magnetic fields. I won't say constant. Magnetic field will keep velocity constant, but electric field will try to pull down. So its velocity will increase. It goes in. If the electric field is dominating, it will go down. But in this case, forces are getting cancelled. The resultant force is zero. When resultant force is zero, there is no acceleration in any direction. It has to go in straight line with constant velocity only here in this case. But if they are not equal, then I am telling, then electric field will be dominating, magnetic field will be dominating, then particle will not go in straight line in that case. So when both forces are equal and forces are getting cancelled, no doubt its velocity will be constant, it will be going in straight line. No force is acting, the velocity will be equal to the ratio of an electric and magnetic fields. That is the point here. Sorry. Next, second, in case all possibilities are there, maybe magnetic field is greater, force exerted by magnetic field is greater than the force exerted by the electric field. So then BQV sine 90 is greater than EQ. Then for velocity is greater than E by B. If the velocity is greater than E by B, what happens now? Or if FB is greater than FE, what happens now? Both are same. So this force is dominating than this force. Therefore, the resultant force will be acting upward. For example, this is 10 newtons, this is only 5 newtons. The resultant force will be acting in upward direction. Now the particle will go like this. Parabolic path here. The path is parabolic. Parabolic. Next, third case. In third case, I will take now FB less than FE. FB less than FE means electric field is dominating, no doubt. So then BQV is less than EQ. Therefore, velocity is less than E by B. So who is dominating now? Electric field is dominating because it is exerting greater force. So particle will be going downwards now in parabolic path like this. So 3 answers. If the particle goes in straight line under this condition I am telling, definitely forces have cancelled. Then it will move with a constant velocity v is equal to E by B in straight line, as if no field is there. First point. Second, if force exerted by magnetic field is greater than EQ, it goes in a parabolic path in upward direction, opposite to the electric field. If force exerted by the magnetic field is less than electric field and electric field is dominating, then it will move in the direction of electric field in parabolic path. So these 3 answers are final. So this is how the particle will be moving. There are so many possibilities, I said. See, I can change the direction of electric field, I can change the direction of magnetic field, I can change the direction of velocity of a particle. So many cases will come here. It is endless. You should know how to solve it, that's it. Okay? So a Lorentz force is sum of both forces is called Lorentz force. Thank you.